BF Day proudly presents Mr. M's Math Games and Math Breakthroughs.
Hello and welcome to episode 15 of Mr. M's Math Games and Math Breakthroughs. It's so great to see you. So you just came back from playing some games with your classmates, and now you're watching this. So that was the math games part of Mr. M's Math Games and Math Breakthroughs. The breakthrough that you're gonna learn about is cryptography, which is the science and math of sending secret messages, whether that's way back in the day or through banks and through the internet and through numbers and computers. So we're going to watch two videos on cryptography, and then you'll answer a flipgrid question, and then you'll be done for today. So you already did the math games. So I'm really excited about the math games, and that worked out because I did a impromptu question yesterday. I asked some of the 4th and 5th graders, what's your favorite Wednesday activity? And everybody kind of liked all of it. Some of you liked the videos, some of you liked the one-on-one games, but the majority of you really liked playing math games with other people. So I'm gonna throw that in here. I threw that in there for today. So I hope you had fun with that today. So without further ado, here is the first video on cryptography.
If you and I wanted to, let's say, pass notes in class, such that if anyone opened the note up, they would have no idea what it said, but we could still figure it out, there's several methods for doing this. For example, maybe beforehand we could agree on shifting all the letters by 3 in order to encrypt our message, otherwise known as the Caesar cipher. So if I wanted to say hello, I'd write a word with those same letters shifted by 3. Instead of H, I'd write K, since K is 1, 2, 3 letters past H. Instead of E, I'd write H, L goes to O, and O goes to R. So this is the encrypted message that I send you. Then when you receive this note, all you do is shift the letters 3 to the left and you get the original message back. But this is too simple since someone could just try a bunch of shifts and figure out what the original message was. But hopefully you can see the foundations of cryptography are pretty simple. You have some message you want to send, or the plain text like hello, and you encrypt this to create a bunch of gibberish, otherwise known as the ciphertext that we saw earlier. This is then decrypted back to plain text, and this is what we just did using our specific encryption and decryption algorithm of shifting by 3. But let's do something else instead. Let's come up with a secret word or key that will swap around the letters for us. For this scenario, let's just say our secret key is computer. And now I want to encrypt the message, "You can trust me." Well, since the message is longer than the key, I'll just rewrite the key repeatedly until the end. And now what you do is really just add the letters. C is the 3rd letter of the alphabet, so we gotta go 3 past Y. Now, since Y is at the end, all we do is wrap around back to A. So we go 3 letters past Y, wrap around, and land at B. O is the 15th letter. If we add O or another 15, we get 30. And to figure out the letter more quickly, remember that Z is the 26th letter. So you could say 27 corresponds to A, 28 with B, which would make 30 go with D. And we can do this for the rest of the message to get our ciphertext. To decrypt it, you would just subtract by the secret key. Now that wrapping around we just saw is actually the start of the real math I'm going to get into soon. So we just saw the 25th letter Y plus the 3rd letter C gave us B, which is the 2nd letter. But we really know that 25 plus 3 is in fact 28. In fact, we could say that 28 corresponds with 2, and we'll use this symbol to show that. But this works specifically for the 26-letter alphabet. And this is the same math you do as with the 12-hour clock. If it's 11 o'clock, disregarding AM or PM, what time will it be in 3 hours? Well, obviously it will be 2. But 11 plus 3 is really 14. So 14 corresponds with 2 on a 12-hour clock, because just like with the alphabet, you wrap around to the beginning. Now, the official way to write and say all of this is 14 is congruent to 2 modulo 12. The visual way to think about this is if the integers continue to wrap around a clock, 14 and 2 would land at the same place. In fact, if we kept going, 26 would also land there, which means 26 is congruent to 14 as well as 2 modulo 12. Then algebraically, the reason 26 is congruent to 2 mod 12 is because if you subtract 26 and 2, the result is divisible by 12. Or you can see that 20 is congruent to 8 mod 12, since 20 minus 8 is divisible by 12. Same goes for all these pairs of numbers on the clock. So this is where we're headed. And I'm going to get back to this soon, but this is the beginning of number theory, the main branch of mathematics used for cryptography. But first, the encryption we were just using is known as the Vigenère cipher, which was used during the 16th century. However, there's a problem with it though. If we used our secret key many times, like over hundreds of messages, an adversary could intercept those, and using frequency analysis, they could eventually decipher what our original messages were. In the English language, the most popular letter is E, which comes up about 12.7% of the time. Next up is T, which comes up about 9.1%. Then A, which comes up about 8.1%, followed by O, and so on. I was curious about this, so I found an online frequency analysis tool and copied in the first chapter of Harry Potter. And the most popular letters corresponded pretty accurately. O and A were just a little mixed up, but yeah, using this, there are ways to crack the Vigenère cipher over many, many messages. You can see that having a key is important in cryptography. So now let's talk about key exchange, or how to establish a secret key when you have to exchange it with someone over a public channel. So I'll start this with a question. A friend and I want to share a secret key, or in this case, a secret number. Now, the problem is there's an eavesdropper who can see or hear anything that we say or write or whatever. Okay, literally anything. We can't use another language, we can't whisper to each other, nothing like that. And let's say it's a new friend, so you guys don't know much about each other. Now, the question is this task even possible? To come up with a secret key that only you two can understand, but the eavesdropper cannot? We'll give that some thought, because now we've reached a point where we need the real math that I want to talk about, or number theory, aka the study of integers.
Alright, so I stopped the video there. I know some of you might be curious to watching the rest. I will put the link to that rest of the video in the bottom, but it gets a little complicated actually. So I know it was starting to get a little complicated towards the end there, but if you want to watch the rest, you can go to the link in the bottom and watch the rest of it. But here's the next one that goes into detail about how banks send secret messages. So here's the second one.
So I've got a very big number to show you today, used by NatWest Bank, so that you can send them your secret bank details. It starts 2, 3, 4, 5, 3, 6, 7, 6, 2, 8, 0, 6, 5, 6, 0, 1, 6, 5, 8, 0, 6, 5, 0, 0, 6, 5, 2, 9, 0, 8, 0, 6, 2, 8, 7, 7, 4, 1, 7. Did you get that, or do you want me to repeat it? So this number that we are reading out is 617 digits long. All banks have similar numbers when you want to send them your credit card details. This is not a secret number. In fact, your computer will download this number when it wants to send your credit card details. It's there to find. This is public. So this code that they use on the internet is called RSA. It's named after the three people who came up with it, who were Rivest, Shamir, Adelman. Shall I show you how it works?
Please.
All right. Imagine if you had a secret that you wanted to send to the bank. So the bank provides you with a box, and it provides you with a key to lock the box. So you can put your secret inside and you can lock it. And then you can send the secret to the bank. That's good, isn't it? But the problem is, if the bank is giving everyone one of these boxes and a key that goes with it, then that means that, well, one person could steal someone else's box and use the key to unlock it and read their secrets. That would be terrible. We can't do that. So what the banks do, same sort of idea, but instead of giving out keys, they give out padlocks. So they give everyone a box. If you've got a secret, put it inside the box, lock it, not with a key, but with a padlock. It goes click, it snaps shut. Once it's locked and snapped shut, you don't have the padlock key. So you can't reverse it, you can't open it up. So if someone steals your box, they don't have the key either. They've got a padlock, but they don't have the key to open the padlock. The only person that does is the bank themselves. And it's a way to send secret messages without having to send out the keys. It's easy to lock the code, but it's hard to unlock the code. First of all, I have to explain this with the smallest example I can, and then I'll show you why we use that massive number. Let's say you're the bank, and you give out two numbers. They're public, so everyone can know them. They're not secret numbers. I'm going to choose the number 3 and the number 10. The bank also has a secret number. Hit this bank's secret number. For now, you don't know what it is. No one knows what that is. Only the bank knows what that secret number is. I had a very bad breakfast this morning, so I'm going to send the message, bad chef. The first thing you do, if you have a message like that, is to turn the letters into numbers. That's quite simple. A is 1, B is 2, and Z is 26. Simple stuff. C is 3, D is 4. Now I'm going to turn it into a code, and I'm going to use the number 3. Now there are some codes that would just add 3. Or there are some codes that would multiply by 3. What we're going to do is raise to the power 3. So we're going to cube these numbers here. Let's do that. So I get 2 cubed, which is 8. 1 cubed, which is 1. 5 cubed is 125. And 6 cubed, 216. The final step is to use the second number, the number 10. I'm going to divide by 10, and I'm going to look at the remainder. So if I take something like 512, when I divide by 10, there will be 51 tens, and then 2 left over. So that's just 2. 5 here, 1 and 4. And that's your code, and that's what you would send. The bank, or the person who's going to decode this message, has a secret number. Now the secret number is, in this example, is going to be 3. There's a formula to work out the secret number. I'm going to gloss over that for a second, but I'm going to show you what to do next to decode the message. This is my code. I'll write it out again. I'm going to do the same thing I did before. This time I'm going to use my secret number. It doesn't have to be the same as 3, but it just happens to be the same as the 3 we used before. But never mind, it doesn't have to be. But I'm going to cube again. So I cube these numbers. We do like we did before. We divide by 10 and find the remainder. And then the decoder will turn that into letters, which is B, and he gets the message back again, bad chef. Now that's just a taste of how it works. That's the process that your computer does every time you buy something on Amazon or eBay. One of the important numbers in this code was this 10. Now this 10 was made by multiplying 2 prime numbers together. 2 times 5 are prime numbers, multiply them together and you get 10. Now that massive number that I showed you that NatWest uses, it's the same idea. It's 2 massive prime numbers multiplied together. That's what it is. If you want to work out the decode key, the secret key, you need to know the original prime numbers. Now the only way a spy, someone who wants to break the code, could work out the original prime numbers is to take that massive number and factorize it, turn it back, break it up into the original 2 prime numbers. This is really hard. So hard that it's impractical to break with modern technology. The massive number I showed you was a 2048-bit number. That means it's about 2 to the power 2048. Now, about a decade ago, we did manage to break 512-bit numbers. We were able to take that number and factorize it into its original primes. A few years ago, a team of academics managed to break a 768-bit number. It took this team of academics with all their resources 2 years to break a 768-bit key. And they said that to break what we use now, which is about 1024, would take thousands of times longer. But given the speed of technology, they reckon that this sort of code, 1024-bit, could be broken within a few years, they said. They said that a few years ago. So this should now start to be replaced. Gmail still uses this, but this should be replaced. And as you can see, NatWest have done that, other banks have done that. They are now using 2048-bit number, which again would take computers, and I mean even with a proper attack, big computers, it would still take them thousands of years to factorize that number into its original prime numbers. Now, hidden in the details for this code is a mathematical fact that was worked out in the 17th century by Pierre de Fermat. He's famous for Fermat's last theorem. Well, this was Fermat's little theorem. If I take a number, a whole number, an integer, any number, call it x. I'm going to raise it to a power, and it's going to be a prime number, so p for prime. I'm going to raise it to a power, and I'm going to take away x. This is a multiple of p, the prime number. Let me do an example. What I mean is if you took a number like 4, and then I took a prime number like 5, and then I take away 4, I would get 4 to the power 5, which is 1024. Take away 4, which is 1020. And that is a multiple of 5, but that would be guaranteed. You're guaranteed to have a multiple of 5. Now, you can imagine that in the 17th century, when Fermat came up with this fact, that people said, well, very nice mathematical fact, but that's pretty useless. Well, what use are you going to have for that? And then suddenly the internet comes along, and it's massively useful. In fact, our whole modern world depends on this fact.
All right, so your Flipgrid question for today is, what would be the benefit of encrypting a message or encrypting your information to the bank? What is the benefit of kind of keeping your privacy? Why do you think it would be important for us now to send secret messages? And also, why do you think it was important for people back then? So answer that question on the Flipgrid. I'm excited to hear your responses, and I will see you all tomorrow. Bye.